All right, so I wanted to make this video that will give us a bit more intuition in terms of understanding what a basis for a subspace is. And so I'll recall this definition that we talked about last class and in the videos for last class, which said that if I have a subspace H, a subspace of Rn, then a basis for H is a set of linearly independent vectors in H that spans H. And so what this means is that, let's say I have a basis for H and it's some set of vectors v1, v2, up to vp. And let's say this is a basis for a subspace H. Then what this means is that if U is a vector in H, then U is equal to some linear combination of these vectors in the basis. C2, V2, up to CP, VP. Or we could also write that H is equal to the span of this collection of vectors. And one other thing to emphasize is that, again, by this definition, these vectors v1 through vp are all linearly independent. And so what I want to talk about in this video is maybe some intuition for why something like this is nice as a description. And in order to do that, I want to kind of step back from vectors for a minute and just talk about numbers themselves. And so if I have this set of positive integers, then this is the set 1, 2, 3, 4, and so on. And if I have the set of positive even integers, this is the set 2, 4, 6, 8. And I'm going to use this symbol. So Z is the symbol for integers, just like R is the symbol for real numbers. And if I put a plus on top of it, then that's this 1, 2, 3, 4, and so on. Okay, so let's say that I have this nice symbol for positive integers. Let's say I want to describe this set of even integers. And so one way to do this would be to say that even integers are equal to the set 2 times k, such that k is an element in here, in this set of positive integers. And so if k is 1, then I get 2. And if k is 2, then I get 4. If k is 3, then I get 6, and so on. But one other way to describe this, I could also say that the even integers is equal to the set 2k, such that k is in Z, and also for L, such that L is in Z. So I could describe it in both ways. And if I do that, this 2k, such that k is in B plus, that gives me 2, 4, 6, 8, 10, 12, and so on. And this set for L, such that L is a positive integer, gives me, when L is 1, this is 4. When L is 2, this is 8. And when L is 3, this is 12. And when it's 4, this is 16. And notice, so this second kind of description here, it doesn't get me every even integer, but it still gets me some. But the thing is that this collection up here does get everything. And so it makes it so that the second set, if I include it in the description, it's not adding anything. So notice the first thing here is this 4. Well, that 4 is up here. And 8's here, but it's also here. 12's here, but it's also here. 16's here, but it's also would be here if I had written it. And so the 4L description doesn't add anything. And so if I wanted to describe the even integers, the most efficient way to do that is with this first description up here, and so to not include this. And even though this is integers, I can sort of think of this description as 2 times k as sort of, in some sense, combinations, linear combinations of 2. It's multiples of 2. Just like if I go up here and I look at my subspace H, I'm saying that U is combinations of the vectors that are in the basis. And so here, these vectors v1 through vp are acting like this description of a 2. And but with a basis, I want to do it the most efficient way possible. So like with the integers, I just wanted multiples of 2. I didn't need multiples of 2 and 4. And so I can describe any subspace if I'm describing it as the span of a collection of vectors. Well, then I can do that with any number of vectors, but my basis is what allows me to do that. It's the most efficient description. And so I want them to be linearly independent. And what this kind of hints at is that if I have a set of linearly dependent vectors, then some of those vectors are excess, aka they're acting like the 4 in the example below. And so what I want to do is revisit this example that we had from class where we had a matrix, and I think it was matrix D, so I'll write that, forgive me if it wasn't. And it was equal to the following, so 1, 3, 3, 2, minus 9, and minus 2, minus 2, 2, minus 8, 2, and 3, 4, minus 1, 11, minus 8. And then we had this extra row that I had forgotten to write, which was 2, 3, 0, 7, 1. And let me refer to this as maybe column, I'll say D1, it's vector D1, D2, D3, D4, and D5. And when we put this in reduced row echelon form, so the RREF of D was equal to the following matrix: 1, 0, minus 3, minus 5, 0, 0, 1, 2, minus 1, 0, 0, 0, 0, 0, 1, and then a row of all zeros. And we identified that we had pivots in the first, second, and fifth columns. So, and then we said that implies that these three columns, first, second, fifth, formed a basis for the column space of this matrix. So we said this implies that D1, D2, and D5 in the original matrix correspond to the vectors forming the basis for the column space of D. And so here, by definition, we know, by definition, the column space of D is equal to the span of all of its columns, so D1, D2, D3, D4, and D5. But what this above tells us is that this is actually equal to the span of just D1, D2, and D5. So this D3 and D4 column are extra. They're acting like the 4 in the example. And so what I want to do here is actually show that in fact the 3 and the 4 are extra, meaning that those columns can be written as linear combinations of the other 3 columns. So I'll work out the first one. So claim D3, the third column, is, I'll say, extra, aka does not need to be included in the basis for the column space of D, and that's because D3 is a linear, or D3 can be written as a linear combination of columns D1, D2, and D5. And so if I wanted to test something like that, this is equivalent to solving the system where I have a matrix associated with just these 3 columns and then D3 in the sort of last row. So let me let a matrix A be equal to D1, D2, and D5. Then this claim is equivalent to solving AX equals D3. And so to that end, let me set up my augmented matrix. So I have D1, which was 1 minus 2, 3, 2, and D2, which is 3 minus 2, 4, 3, and then D5, which is minus 9, 2, minus 8, and 1. And then I want to set this equal to the third column, this D3, which is 2, minus 8, 11, and, oh, sorry, that's D4. Sorry. This D3 is 3, 2, minus 1, and 0. And if I do that, and I row reduce this, I end up with the following. So I have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And then I have a minus 3, 2, 0, 0. And this tells me that D3 can be written as a linear combination of, in fact, only the first two are necessary, and it's minus 3 times D1 plus 2 times D2, and then 0 times D5, but I won't write that. And so that shows that this claim above here is true, and since D3 can be written as a linear combination of these basis vectors, it's not necessary to include it in our basis. And I'll say that, in fact, the same thing ends up happening with D4, and if you follow the same process, it is equal to 5 times D1 minus D2. And I'll scroll up here and point out that in our row reduced matrix, I have, this is sort of where D3 was, and this is where D4 was, and it is not coincidence that I have the minus 3 and the 2 and the minus 5. And then, sorry, that should be, I think that should, one of these should be a positive 5. Doesn't matter. Okay, I'll sort that out later. Either way, the point is if you reduce this matrix, then you should get the following. And so what that tells us again is that these 3 columns are, or these 2 columns are extra, and so we can use the other 3 as the basis for our column space, and we don't need these others.